So hello everyone again. So our speaker today is Professor Michel Théra from the University of Limoges. His talk is about the old and new resource on equilibrium and quasi-equilibrium problems. So please, Professor, this is your space.
Okay, thank you very much. Hello everybody. Hope you are well. And as you can observe, after a long lockdown, I am going well. And I would like first to thank you very much, all the organizers, for
It looks like Michel is muted.
Okay.
Okay.
Ah, oh la 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 la. Sorry, excuse me. We have to. Ah la 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 la.
Now it's okay.
Yes, yeah, we can hear you. Sorry.
Ah la 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 la.
Yeah, we can.
Michel, everything is okay. Please continue.
Yeah. Please continue.
Okay. So because I see some other thing in my screen, anniversary and so on and so on. Okay. So today I will. I want to. I don't know if you have. If you listen to me correctly, but I said that after a long lockdown, I am going well, and also I would like to thank very much all the organizers of this webinar for the invitation to give a talk today. And today I will speak about all the new results on equilibrium and quasi-equilibrium problems. And it is a joint work with two Peruvian colleagues, John Cotrina and Javier Zuniga. And this work has been submitted to JOTA very recently. And the outline of my talk is the following. I will start with a short history about this kind of problems, give some example. Then I will give some hints about the tools I am using, tools which that maybe you don't know very well. For instance, the concept of transfer lower continuity, and also some variational type principle for big functions. Then I will speak about equilibrium problems, give definition examples and quasi-equilibrium problems. And finally, if I have enough time, I will talk about the system of quasi-equilibrium problems. Okay. And as I told at the very beginning, it's a joint talk with two nice colleagues from Lima in Peru, John Cotrina and Javier Zuniga. And the paper, you can read the paper. I can send you the PDF if you ask me, but also if you log to this site, which is a site from the French NRS in France, you can obtain the paper easily. Okay, so I will start with a short history and the motivation. And if C is a non-empty subset of a topological space X, and F is a bifunction. By bifunction, I mean a function of two variables from C times C to R. And an equilibrium problem is a problem of finding X in C such that f of X and Y is positive for every Y in C. And this kind of problem goes back to the celebrated Knassner-Kuratowski-Mazurkiewicz in 1929, and also its generalization in finite dimension by Ki-Fan in 1961, and its extension by Brezis-Niremberg Stampacchia to a subset which is not necessarily compact by using what they call the coercivity type condition. And nowadays, great interest is given to the convergence analysis of iterative methods to reach solution of these equilibrium problems. And if you remember, Key-Fan minimax principle, 1972, the theorem is the following. We assume C is a compact and convex subset of Hausdorff topological vector space. And we suppose given a bifunction from C times C to R, we satisfy three conditions. The first one, f of xx is less than equal to 0 on the diagonal for every x in C. And for every x in C, the set of y in C, such as f of x and y is strictly positive, is convex, and for every x in C. And for every y fixed in C, the function is the lower semi-continuous with respect to the first variable, x. And if these three conditions are satisfied, then Fan proves that there exists x0 in C, such that f of x0 and y is less than equal to 0 for every y in C. And after this result given by Key-Fan, with the goal to apply equilibrium problem to variational inequality. In this case, we replace the function f of x and y is the scalar product, for instance, of ax with x minus y, where A is an operator which is monotone or pseudo-monotone, but the kind of monotonicity. And Brezis-Niremberg and Stampacchia extended the Fan's result to the following. It was in 2008. They supposed the condition 1 and 2. Remember 1 and 2, these two conditions. And furthermore, they supposed that 3' is satisfied for every fixed y in C. The function is lower semi-continuous on the intersection of C with a finite dimensional subspace X. And condition 4, whenever X and Y are in C and Xi is net on C converging to X, then we have this implication given in red. If you have the first part of this, f of x, y, and 1 minus tx plus ty less than equal to 0 for every t between 0 and 1, then necessarily f at x and y is less than equal to 0. And also, finally, condition 5, that there is a compact subset L of x and y0 in the intersection of L and C, such that f of x and y naught is strictly positive for every x in C when y naught doesn't belong to L. And if all these conditions are satisfied, they prove that there is x such that f of x naught and y is less than equal to 0 for every y in C. And in particular, you have that the infimum over x in C of the supremum over y in C of f of x and y is less than equal to 0. And the proof they give is based on the Knastner-Kuratowski-Mazurkiewicz result I just mentioned before. And this theorem, Brezis-Niremberg-Stampacchia, implies, for instance, the known fundamental sign minimax principle, as well as the Hartmann-Stampacchia theorem for existence of solution to variational inequalities. And to continue the history, Umberto Mosco, an Italian mathematician, very well known and famous, mostly in PDEs, introduced the implicit variational problem, nowadays known as quasi-equilibrium problem. And just remember the Bloom and Utley work, who proposed a mixed version of Kifan minimax inequality by perturbing the monotone objective bifunction by a non-monotone term. And their work covers further problems such as non-convex and non-smooth Panagiotopoulos inequalities considered by, for instance, Shadley and Riai and many other people. Also, Ait Mansour and Riai studied, for example, the quantitative stability of equilibrium problem, and also relaxed generalized quasi-monotonicity, quasi-convexity, for example, were studied by Castellani and Giuli, Adjizavas, Bianchi, Casai, Pini, and many others, including people attending my talk today. And also, I want to mention iterative method for equilibrium problem. People like Mudafi extended the proximal point algorithm from variational inequality to equilibrium problem. And we have many, many other, and these people, I can mention many other names that are not given here. Italian people, also Wilfredo Souza, in the audience, Martinez Logan, and many other people. Okay, so example. Now, the first example is the minimization problem. If you have a non-empty subset C of Rn and a function h and t, I don't need t, by the way. This is a wrong thing. The minimization problem associated to h and c consists of finding h of a point such that f of x is less than or equal to h of y, or y than c, and this can be shown as a view, as equilibrium problem if you take the function f of x and y equal h of x minus h of y, and x bar solves this minimization problem if and only if x bar solves the equilibrium problem associated to f and c. Another example is the Stampacchia variational inequality associated to an operator t. And this problem consists on finding x in C such that this part red, x bar in C, and also C bar in T of x. T is a set value mapping such that this scalar product x bar with y minus x bar is positive for every y in C. And we can see this as also as an equilibrium problem. If you take this function f of x and y equals the max of xi minus y, of xi applied to y minus z for every xi in T of x. And x bar solves this Stampacchia variational inequality if and only if x bar solves the equilibrium problem. Okay, now maybe I can speak also about the saddle problem. For this problem, you have two x-bar space H1 and H2, two set C1 in H1 and C2 in H2, two closed convex subset, and we say that the pair x1, x2 is a saddle point of theta, a function which is defined on C1 times C2, if and only if theta of x1v is less than or equal to theta of u x2 for every uv in C1 times C2. And in this case, you take C, the product of C1 by C2, and F, the function given by F of X, parenthesis is missing, F of X1, X2, Y1, Y2 equal theta of Y1, X2 minus theta of X1, Y2. And by taking this function F, this B function, defined on the C1 times C2, then the equilibrium problem associated to F is equivalent to the saddle point associated to theta. And finally, I will give another example, which is the so-called Nash equilibrium problem. Many of you know this kind of problem. You have a finite index set I, and every player I has a strategy, okay, and Ci, and you set, if you set Ci the product of the C, the product of all the Ci, this is the product of the strategy sets, and for each Y you have a loss function Fi, and if you define F from C, the product, the strategy sets to R, which is defined by F of X equal the F1 of X times Fn of X, you have n players. And if you define, this is a notation C minus Y minus I, this product of the strategy sets, but when G is different of I, and this is a notation, then you define for X and Y, this X of Y, or X of Yi as the following. Then X bar is a Nash equilibrium for if for all I, there holds this inequality. And if you take this function defined in red, F of X and Y, the sum of F of X, Y, minus F of I of X, then we can observe that X bar is a Nash equilibrium if and only if X bar solves the equilibrium problem associated to F. So as you see, you have many examples where equilibrium problem apply. Okay, so now I want to continue by giving some information about the tool I will use and that are used in many papers related to this subject. So in 1995, two colleagues, Tian and Zhu, were interested, they published a paper in the Journal of Mathematical Economics where they were interested in the question to know under what minimal condition a function attains its maximum on a compact set. The set of maximum points of a function on a compact set is non-empty, and the maximum correspondence is closed. And for this, define the concept of transfer lower continuity. And we will say that a function h from C to R union plus infinity extended real valued is transfer lower continuous if for every x and y in C such that h of x is strictly greater than h of y, there exists y prime in C and a neighborhood v of x such that h of x prime is strictly greater than h of y prime for every x prime in the intersection of C with v of x. And we have also defined also the concept of transfer weakly lower continuity for the same definition, but instead of the strict inequality, you have greater than equal to I don't know what to say, it's not strict, it's strictly greater or equal to h of y prime. Okay, and in fact, with this, they prove Weierstrass type theorem. If C is a compact subset of a topological space X and F is an external real valued on C, then F attains its minimum on C if and only if F is transfer weakly lower continuous, TLC. And also, they prove that if C is a compact subset of a topological space and for an external real valued function defined on C, then the minimum of F is non-empty and compact if and only if F is a weakly transfer continuous. And in fact, if you are using the level set of functions, we can prove this, and by using this, we can prove enough easily the theorem I have just mentioned. But contrary to lower semi-continuity, transfer lower continuity is not stable under addition. For instance, if you take this function with the figure, the drawing below, you see that H and G are transfer lower continuous, but the sum H plus G fails to be transfer lower continuous at the origin. And it can be seen through the graph represented here. So there are some problems with transfer lower continuity. Now I want to speak briefly about something you know very well. It's lower semi-continuous regularization. When you have a function H, you have its epigraph, and you can define the largest lower semi-continuous minimum of H, which is called the lower semi-continuous regularization. And in fact, the epigraph of this regularization is exactly the closure of the epigraph of the function. And through this definition and using the concept of lower semi-continuity, you can see that the lower semi-continuous regularization H bar of H is exactly defined by the limit inf of H of Y when Y goes to X. And you have a well-known fact, I will remind them very quickly. H bar of X is exactly defined as the infimum of lambda in R, where X belongs to the closure of the section of S lambda of H. Of course, H bar of X is less than or equal to H of X, and so on and so on. Okay, so this is very well known. And I don't know if you know this definition. A lower semi-continuous regularization is well defined. Is H bar of X is greater, doesn't take the value minus infinity, because as you see in the definition, this function can take the value in general, can take the value minus infinity. But if it doesn't take the value minus infinity, then we say that the lower semi-continuous regularization H bar is well defined. It means, in other words, that H admits the function H admits a lower semi-continuous minorant. And we have this proposition: if C is a non-empty subset of a topological space X and H is a function defined on C, then if H is transfer lower continuous, then its lower semi-continuous regularization H bar is well defined. This is an example of well-defined lower semi-continuous regularization. Okay, I skip the proof. And also, the following result is known. If C is a non-empty subset of a topological space X and H is a function defined on C, then the infimum of H of X on C is equal to the infimum of H bar of X on C. And also, the argmin of H is equal to the argmin of H bar if and only if H is transfer lower continuous. Okay, and this result is important. Okay, and transfer lower continuity is essential, for instance, in this result here. Okay, because if you take this function H of X defined by the absolute value of X for X different 0 and in 0 is equal to 1, okay, and you see that the argmin of H is equal to is an empty set, and the argmin of H bar is equal to 0. Okay, so you don't have this inequality, but it means that H, as you see, H is not transfer lower continuous. Another proposition, if C is a non-empty subset of a topological space X, okay, and H is a function defined on C, if there is some X in C such that H bar of X is less than equal to H bar of Y for every Y in C, then X is necessarily a minimum point of H. Okay, and this is really easy to prove. Now, another tool I will use for what follows is Ekeland variational principle for bifunctions. So there are many results related to extension of Ekeland variational principle for bifunction. I did myself one with Utley in 1993, but you have, for instance, Bianchi et al., Aleš and Radulescu, and many other results of this type. And this approach, the approach given in all these results is based on the assumption that the equilibrium bifunction should satisfy the triangle inequality, which is in red, which means that if you take X, Y, and Z in C, you have that f of X and Y is less than equal to f of S and Z plus f of Z and Y. And one of the results, for instance, has been given by Castellani and Giuli. It is the following. If C is a non-empty closed subset of a complete metric space X, D, and if F is a bifunction defined on C times C, if you assume that there is a function H bounded from below and lower semi-continuous, such that H of Y minus H of X is less than equal to F of X and Y. So F of X and Y is bounded below by this of H by H of Y minus H of X. For every Y and X in C, then for every epsilon positive, strictly positive, and for every X0 in C, you have X bar in C such that these two conditions A and B are satisfied. H bar of X is less than equal to H of X0 minus epsilon, the distance between X0 and X bar. And condition B, F of X bar and Y plus epsilon, the distance of X bar and Y is strictly positive for every Y different from X bar and Y in C. And if you take as a bifunction, for instance, not for instance, if you take as a bifunction F of X and Y, phi minus X phi x minus phi of y, you recover the original Ekeland theorem for phi, okay? And this result was given by Castellani and Giuli. No, sorry. And now we can restate the Ekeland variational principle in terms of lower semi-continuous regularization. Always C is a non-empty closed subset of a complete metric space. The completeness is necessary, as you know, when you are talking about Ekeland variational principle. And H is a function which is bounded from below. Also bounded from below is very important. For every epsilon positive and for any x0 in C, you may find x hat in C such that these two things happen. H bar of x hat plus epsilon, the distance between x0 and x hat is less than or equal to h of x naught, and also for every y different from x naught, you have that h of x plus epsilon, the distance between x and x hat, is strictly greater than h bar of x hat. And in fact, all the theorems I have mentioned are equivalent. Okay? This. And as a corollary, we have the following. Now C is always a closed subset of a complete metric space. F is a bifunction, and you assume that there exists a bifunction J satisfying J is less than or equal to F. J is bounded from below and lowers to be continuous with respect to its second argument. J vanishes on the diagonal of C times C, and J satisfies the triangle inequality property. Then, in this case, you have this result that for every epsilon strictly positive and all x naught in C, there exists x hat in C such that g of x naught and x hat plus epsilon, the distance between x0 and x hat, is less than or equal to 0. And the f of x hat and x plus epsilon, the distance between x and x naught, is strictly positive for every x different by x hat. And now, so the triangle inequality I already gave. There is also the definition of what is called cyclically monotonicity. And it has been, I think, not completely sure, defined by Bianchi, Casai, and Pini. And it reads that as follows. If you have x1, x1 such that then you have that the sum of xi and xi plus 1 is less than or equal to 0. And in fact, this concept of cyclic monotonicity extends the classical definition from Rockefeller even for set volume mapping, for instance, operators. And also very classical monotonicity of the bifunction. You know that. And also the concept of pseudo-monotonicity, which is well known for people who are working on this kind of problem related to bifunctions. And I know that there are plenty in this audience. For instance, Juan Enrique, Sosa, and many others. Okay, example of such properties I will give an example from Ajizavas and Katibadzadeh in 2007. If C is a convex subset of a topology space X and H a function which is which has a well-defined lower semi-continuous regularization, you consider these two functions, g of x and y equal h of y minus x, and f of x and y equal h bar of y minus h of x. F is cyclically monotone, sorry, and G satisfies the triangularity property. Okay, so it's very easy to verify. And cyclic monotonicity of f hat. F hat is a function defined by f hat of x and y equal minus of f of y and x. And cyclic monotonicity of f hat is equivalent to the existence of a function h, such that f hat of x and y is less than equal to h of y minus h of x for every x and y in C. And we can see also, in addition, that if f is monotone, then f of x and y is equal to h of y minus h of x, and it implies that f is cyclically monotone. Okay? So this I already gave at the very beginning. So the equilibrium problem I define just when I start my talk, but also I didn't say that at the beginning of my talk. We can define also what we call the Minty equilibrium problem, which is the problem like this: find the x in C such that f of y and x, you mix the variable, less than equal to 0 for every y in C. And in fact, you see that if you use this function f hat defined just before, equilibrium problem is the same that Minty equilibrium problem for f hat. And okay. And also you have this connection with the admin of H, which is in between the solution set of equilibrium problem, Minty equilibrium problem, and equilibrium problem. And also, if F epsilon monotone, then the above inclusions are in fact equalities. Okay, so if a bifunction vanishes on the diagonal, then you have that if x is an equilibrium problem, that it's equivalent to x belongs to the admin of f of the second variable for x, and for the minties of argmax, of course, and also the set of equilibrium problem is included in the union when C belongs to, when X belongs to C of the admin of f of X with respect to the second variable Y. Okay, and also another result which gives the fact that the equilibrium problem is non-empty when C is compact, non-empty, and f is a bifunction such that there exists a transfer lower continuous function h satisfying this inequality in red, f of x and y is greater than h of y minus h of x. Okay, so now I want to talk about a quasi-equilibrium problem. If now C is a subset, a given subset in Rn, sorry, and you have a set value mapping K from C to C, and a function f, a bifunction, okay, on Rn. And the quasi-equilibrium problem associated to F and K is the problem of finding X in K of X. Okay, K of X is a set because K is a set value mapping, such that F of X and Y is positive for every Y in K of X. And okay, you can define similarly the mean-T equilibrium problem. And okay, in this case, clearly, we have that the equilibrium problem is equal, the solution set of the equilibrium problem is equal to the solution set of the mean-T equilibrium problem associated to F hat. And and you have exactly the same thing that I already said. So this I already gave. Sorry, it seems that I've don't remember if I gave this. So this was a reason by Castellini and Giuli, which gives that, I already say that if C is a compact set, then the equilibrium problem is non-empty as soon as you have this result. And this result was given by Castellani and Giuli. I didn't say that. Okay. But instead of considering the transfer lower continuity of H, consider lower semi-continuity. Okay. As a direct consequence, I have this result here. And now I want to give, I think, a new result. Okay, so we have this quasi-equilibrium problem, and we have a first lemma. C is a non-empty subset of a complete metric space. K is a multifunction. H is a function bounded from below. And we assume that this implication holds if for every epsilon positive, strictly positive, and x0 in C, the implication is the following: h bar of x plus epsilon, the distance from x to x naught, is less than or equal to h of x naught. Then you have a point in y in k of x such that h of y plus epsilon, the distance of x and y, is less than or equal to h bar of x. So this is the an assumption, okay? And if this assumption is satisfied, then there exists x hat in fixed point in a fixed point of k. X hat is a fixed point of k. It means that k of x hat belongs to k of x hat is satisfying. So h bar of x hat plus epsilon, the distance of x0 to x hat, is less than or equal to h of x0. And finally, h of x plus epsilon, the distance of x to x hat, is strictly greater than h bar of x hat for every x different from x hat. Okay, and this is a lemma which uses, of course, the previous result on Ekeland variational principle. And from this, we can prove that if C is a non-empty closed subset in a complete metric space X, K is also a self-valued mapping, F also a bifunction, and we suppose that the set of fixed point of the multifunction K is compact and non-empty, and that there exists a transfer lower semi-continuous function bounded below H, such that you have this inequality for every X and Y in C. And you suppose that for every epsilon strictly positive and each x naught in X, this implication holds. Then you can prove that the set of quasi-equilibrium point of f k is non-empty. So it's a condition that these are conditions in order to prove that the quasi-equilibrium problem associated to f and k has a non-empty solution. But we can notice that this result, it is related to a previous result by Castellini and Giuli in 2006, but instead of using the lower semi-continuous, we are using the lower semi-continuity. And as a consequence, which is a weaker notion than the lower semi-continuity. I forgot to tell you that, but you understood. As a direct consequence of this theorem, we have that under the same condition, the set of fixed point of K is compact and non-empty. H is transfer lower semi-continuous and bounded from below. And also important, we are in a complete metric space. C is closed, non-empty and closed. And also the same condition I've given before. Then we have a fixed point of K x hat such that h of x hat is less than or equal to h of x for every x belonging to K of x hat. And finally, I will finish with system of quasi-equilibrium problems. Now, if I is an index set, we consider a complete metric space X, a non-empty family indexed by I of non-empty closed subset Ci, a family of set-valued mappings key i's from Ci to Ci, and we define the set-valued mapping K from C to C by setting the K of X is a product of the Ki of Xi. C is a product of the Ci, and X is equal to the Xi. By a system of quasi-equilibrium problem, we understand the problem of finding X hat in fixed point of K, such that Fi of X hat and Yi is positive for every Y in K of X hat. Okay, we can observe that the set of fixed point of K is a product of the fixed point of Ki. And I will give now a new result, which extends some of the results in the literature. Castellani-Giuli, 2016, Alec and Radulescu, 2015, Bianchi, Casai, Pini, 2005. The theorem is the following: for each I for each index I, so Ci is a closed non-empty subset, and you suppose that the bifunction Fi for each I satisfy this condition in red. Fi of X and Yi is greater than Hi of Yi minus Hi of Xi for every X and Y in C. And you suppose that this function Hi are transfer lower continuous functions bounded from below. then we can prove that the system of equilibrium problem admits at least a solution. Okay, so this extends a little bit previous result given above Castellani-Gioli, Alec Radulescu, Bianchi, Casai, Pini. Remark this condition also here in red is equivalent to this condition here, that the sum of the fi of x g x I sub g of plus 1 is positive, where you have this. And okay, and now if you denote by SEP FICII the solution set of this equation line, I don't see where it is now because it's hidden. And if you define the bifunction f by the equality tent, f of x and y equals the sum of fi of x and yi, you can I don't know where it is now. You can prove that SEP is included in EP. And okay. And finally, also remark that given a finite, assume that I is a finite index set, and if for each I the function fi satisfies this condition, I don't know how to say in English, speak in French. Okay. Then the function f hat is cyclically monotone for this function f defined by this equality tent. Okay. And also we can also define the concept of transfer lower continuity property for a family of I in the following sense. This family is transfer lower continuous if there is a transfer lower continuous function h which satisfies this condition in red, where f is the function defined by the equality tent, the sum of the fi of x and yi. Okay. So if you look at the function f associated to a family of functions with the transfer lower continuity property and defined by this equality tent, then the bifunction f hat is cyclically monotone. We can prove this. And also, if for each I, the function fi is upper semi-continuous in its second argument, then the family of function fi has a transfer lower continuity property, due a result given by Castellani and Gioli. Okay. And we have a final theorem that if you assume that I is finite index sets and the family of function fi has transfer lower continuity property, and if fi of x and xy equals 0 for every x equal xi, x minus y, for y in I in I, then the SEP of FICII admits that is a solution. So it's a existent theorem for the problem SEP. And also about this, maybe it's not so important, that this theorem is not a consequence. It's a result which says that it's not a consequence of this theorem here, which has been given, and which is an extension of the result by Castellani-Gioli, Alec Radulescu, and Bianchi Casai-Pini. Okay. And another theorem, if for each I, we set Ci is a non-empty subset of a complete metric space Xi with a distance di, Ki a family of set-valued mapping, Fi a family of bifunction, which satisfy the condition trèfle, which is trèfle, which was this condition here. Okay. If this condition holds for some transfer lower continuous function hi, which is also bounded from below, and if you assume that the fixed point of K is compact and this condition 2 is satisfied, then you have a solution here to this problem, system of quasi-equilibrium problem. Okay? I think I am over. So a short bibliography. So this the end of this talk, not the beginning, but the end of this talk is related to this paper submitted in 2020. I give the information about Bianchi, Casai, and Pini, Rockefeller, Castellani-Gioli, Algizavas, but of course the bibliography is not complete, and we have used many other results that are not mentioned here. And I thank you very much for your attention. It was an interesting experience for me, a little bit tiring. Okay, and see you soon.
Very fashionable.
Yeah, thank you very much, Michel, for your presentation. So now, is there any questions and discussion for Michel? We already have Marco have posed a question for you.
It's 1 hour talk. Oh, it's too long talk.
Michel.
Hello? I don't hear.
It's a question from Fran's family.
Okay.
Okay, so let's look in our chat. So there's some comments in the chat. Let's start with the chat. And if anybody has a question, please use chat to write it down, okay? And then we can follow some sort of order so we don't all speak together.
Okay. Can you see the chat, Michel?
So otherwise I'm gonna read this for you, or Marco can.
Maybe I can just go through what is written there, right? So the first comment was from Wilfredo, that the Brezis-Niremberg Stampacchia was, I think its first result was in 1972. So I think it was just a comment.
Yeah. Okay, 1972. What I wrote something different, maybe. No, I don't understand the comment.
Wilfredo, do you have any other any clarification on your comment?
I say no. 2008 is not. It's a mistake, of course.
Okay, so it was just a comment. Okay.
Well, I have to change this.
Mm-hmm.
Okay, no, it's cut and paste. No, it's not correct. I agree with Wilfredo.
Okay, so let's move on to the next question. So the next question is from Marco, and Marco, would you like to ask your question, or should I read it?
Yes, why not? Okay, thanks, Vera. Michel, congratulations for your talk. My question concerns for me, these new concepts of weekly TLC. I found these concepts very challenging due to their very interesting properties. Perhaps I miss the relationship among these concepts and ordinary lower semi-continuity. And a second question, or a second part of my question is the following. In relation to the new results, in the last part of your presentation, the new results, these weak TLC are the weakest assumption possible, you think? This is the question.
This, I cannot really answer positively because but it seems to me that it is difficult to weaken again the lower continuity. I mean, it seems to me that it is a minimal thing that we can ask for this kind of result, but maybe I have to work a little bit more on this. But it seems to me, if I want to answer quickly, I think it's a minimal thing that we can ask for that.
Yes, but I'm even more interested in going deep inside the relationship among this TLC, a weekly TLC, with ordinary lower semi-continuity. Can I find information in the paper of Castellani, the last, where is these very nice properties studied and their properties are presented in detail? This is my question. Okay.
So I can send you the original paper by Tian and Zhu because
choice. Okay, thank you very much. Okay.
No, because it is a very interesting paper. In fact, it has been published in the Journal of Economics, and they are using this for in the context of mathematical economics. But it's in fact a mathematical paper. It's a real fine analysis.
I wonder why these nice properties are not exploited in a more intensive way, because the properties of these concepts are very interesting concerning minimization. For instance, the equality between the function h, the minimum of the function h and h bar, I found very interesting. And so this is why my interest is in this direction.
Thank you. Thank you for that. But in fact, I discovered this very recently because I was not aware of this kind of result until the end of last year. I was contacted by these two colleagues from Peru, and they asked me to be involved in their projects. They sent me some notes. And from this, I learned myself because I don't know this before the end of last year.
Okay, thank you. Good morning.
But it's a new things for me because, but I was very interested in cooperating with this project with these two nice colleagues. I think that Wilfredo knows them very well.
Okay. Thank you.
Okay, so thank you very much for this in-depth discussion of those properties. And Alex, do you have anything to add? Because you had you said you had the same question. Do you want to say anything else?
In fact, Marco has asked my question already.
Okay.
It is indeed, it looks like an interesting property, and surprisingly, not many people have used it since the 90s when it was introduced.
Yeah,
or
exactly.
maybe we just don't know. Maybe people are using it.
I think we just didn't know that.
But do you
these
know of
people-
anyone else using this property?
Because the author of this property were not working in the same areas than us, and so sometimes it takes time to be aware of
Yes,
this
sure,
result.
but
Because,
plenty
for
of
example,
people are using standard lower semi-continuity because it's a useful property. This property which you introduced today also looks natural, and I would expect also hundreds of people to use it in various areas of mathematics. But this doesn't seem to be the case. Is it just because people don't know about it, or maybe it's not that useful?
maybe.
Maybe after the referee's reports, you know, Michel will find find out about more people who use them.
Sure. Maybe reviewers are already among the participants of this seminar.
Maybe
there is a reason for the very rare use of these properties. Is the fact that they are, for instance, the sum of two functions enjoying this property fails to have this property. And so can be one reason by which is not used intensively. No sé, is my guess. No?
okay.
So let's move on because there's more questions, and let's try to cover all questions and everybody who wanted to ask questions. So the next question is from Rainier. Rainier?
Hi, hello. Thank you, Michel, for very nice talk. My question is if there's some kind of equilibrium problem that generalize the variational inequality problem when the operator is not point-to-point, when the operator point set.
I don't hear very well.
Sorry. Yeah, but my question is, there is the equilibrium problem, they generalize the problem of the variational inequality problem when the operator is point-to-point. What about when the operator is not point-to-point, it is point-to-set? There is some kind of equilibrium problem, or someone has studied this problem when the, for example, when the bifunction, it is multifunction.
When the bifunction is a multifunction.
Yes.
Yeah, there is in the example slide, there is Michel give example. If you go back to the second or the third slide.
Second slide?
Example slides. Second section. One more. More. No. Here it is. The second, no, the preface.
Of study. The problem when, for try to generalize.
This one. The second one.
Okay, that's right. Okay.
Okay, sweet. SVI.
So here the EP problem at the general line of point-to-set VI.
Exactly.
So say again.
So the final question is about the second example here.
This one. SVI?
Yeah,
Stampacchia variation. And so what you want to know?
That's right. It's exactly the second problem. Because I always see that this equilibrium problem for variation inequality, but not for the point-to-set. And this kind for the point-to-set. That's right. Is answer my question. Thank you very much. Maximo.
Right.
Okay,
Thank you.
thank
So we have one more suggestion from Wilfredo. Wilfredo, are you connected?
Yes, I'm here. Yes, right now it's very important to focus a problem in economy, exchange economy. I think it is easy to transform the problem to find equilibrium price in exchange economy in a quasi-equilibrium problem. Michel, do you have if some people make work about this subject?
Say, I don't know really. People working in economy and
No, if you know some paper considering the problem to find equilibrium price, transforming this problem in quasi-equilibrium problem, do you know if some people working about this problem?
No, but I can check.
Okay. Thank you.
No, I can check. I promise. But for the moment, I cannot answer positively to your question.
Next.
Your question is, if I understand, if I know people working in economy and trying to relate equilibrium price to a quasi-equilibrium problem, is the question?
No. In economy, the people, in order to find equilibrium price, use a fixed point problem.
Yes,
and I think that it's much better work transforming the problem of find equilibrium price in a quasi-equilibrium problem, because in quasi-equilibrium problem you have many properties respect to the functions and the sets. But using the fixed point theory, the problem is that the fixed point problem, the fixed point theorem needs, for example, capacity. Is a very hard assumption there.
Yes. Yes, it is. Okay. This is an interesting question, by the way. Okay, Wilfredo, I will think about it.
So it appears that there's another research direction to explore.
Yeah. No, it's an idea that some people try to work in transform the problem to find equilibrium price in exchange economy in a quasi-equilibrium problem. I think this is a better problem.
You think? But it has not been done for the moment, you think?
Yes, I will try to do, but I try to find in the literature, but no, without exists, to find some paper talking about it.
Okay.
And my question is for you, if you find anything, any paper talking about it.
Okay, I think the best is we keep in touch together about this. It's an interesting problem. Yes.
Yes, and then guys, once you have done it, you're very welcome to give a talk about it.
Okay.
So I think
we can work on it with Wilfredo. Sorry. Okay. Interesting question. Thanks.
So there's just one comment, Michel, from, yeah, so there's several people discussing. There's a small misprint in this slide that is open. It should be it shouldn't be Z, it should be X. So it's in the last equality with f of x, y. There's just a discussion that where it should be, whether it should be y minus x and not minus y minus z, sorry.
Ah oui, okay. So this, it happens. Okay, thank you.
Okay, so the discussion led to correct result.
Okay, well,
Yeah,
not so
made
important.
some progress.
Okay. Okay, I did this as careful as possible, but you have always misprints.
All right, so I think we have no more questions. So I don't see anything in the chat. So
Okay.
Braley says, thank you, Michel.
Okay, thank you so much for the invitation. It was my pleasure to give this talk.